Today we're going to talk about buffers. Buffer solutions are anything that can resist large changes in pH. There are many reasons why you would not want the pH of your solution to change really quickly. I mean, think about it. If you stepped into, say, a hot tub and you're expecting a pH of 7, you're not expecting to get burned. What if water's pH just fluctuated randomly and all of a sudden it was a pH of 3? I think you'd be jumping out of the hot tub really, really quickly. But we don't expect water's pH to change. It's very stable. So what if you have a solution that you know may encounter fluxes in pH through either the addition of a little acid or an addition of a little base? What if you could figure out a way to make it so that you could resist changes in pH and make it so, like when you stop in and jump into a hot tub, you don't have these huge fluctuations in pH. That's what a buffer's job is to keep there from being fluctuations in pH. And so when you have a buffer, then how do you make it? What are the components? Typically, a buffer is prepared by mixing a weak acid and a salt of that weak acid. In today's lecture, we're going to use sodium acetate and acetic acid, the two molecules you see below, as our example. And the whole purpose of using these two, and this would be called an acetate buffer, is that each component can neutralize either an acid or a base. And so if you added a bunch of acid to the solution, it could be neutralized by the basic portion of the buffer. Or if you added a lot of base to the solution, it could be neutralized by the acidic part of the buffer. And so by making it have multiple components, you're able to design a solution that can resist those large changes in pH. So let's look more in detail and see how a buffer solution actually works. So here is our acetic acid, CH3COOH. What happens when you place acetic acid in water? So let's do a neutralization reaction, which you guys have gotten pretty good at. CH3COOH plus water. And I'm going to give it double arrows here because why? Because it's a weak acid, not a strong acid, and so you're going to only have incomplete dissociation. So whenever CH3COOH dissociates in water, what ions are formed? CH3COO minus and H plus. And then if you have these form into water, let's draw the water's Lewis structure. Because remember, water can self-ionize and it's amphoteric, so it can act as either the acid or the base. If water is present with a hydrogen ion, what's it going to act as? It's going to act as the base, because if it has an acid in solution, it's going to form water to act as our base. So instead of water donating a hydroxide in this situation, it's instead going to act as a Lewis base, and it's going to allow our hydrogen to attach to it. Okay? So that means that whenever you put acetic acid into water, what you're going to produce is H3O plus and CH3COO minus. Now the conjugate salt of acetic acid is typically sodium acetate. Why is that? What happens whenever you dissociate sodium acetate? It forms two ions, sodium and CH3COO minus. And so why is that the salt that typically forms from acetic acid? Because it produces the conjugate base that was produced via acetic acid. So what happens is you have these two different molecules here. Acetic acid, that's one, and sodium acetate, this is two. So if you were to put both of them into water, you're going to produce either the acid form or the basic form. Our acid form being acetic acid, or our conjugate base over here. So what happens is if you only had acetic acid in water, you're going to produce a little bit of base. But if you're to throw in a whole bunch of sodium acetate as well, you're going to produce more of the base. And so now whenever you've got this forming a buffer in solution, what can happen is your acid can react with things or your base can react with things. And so you really have two parts of a puzzle that can be built together to really form a really strong, stable pH. So pictorially, here's the example. Where here you have a solution, it's composed of our weak acid, and that being our acetic acid, and its conjugate base, that being our sodium acetate, and its job is to resist change in pH. So sodium is just a spectator ion. You don't really have to use sodium. But if you use acetic acid, you have to use acetate, which is simply the name for our CH3COO-. So what happens over here on the left is what's depicted if you throw a whole bunch of acid into solution. So let's say we've got our acetic acid buffer, our acetate buffer, and we want to throw in a little bit of acid and see if it does its job and resists change in pH. So what literally happens is hydrogen ions, the ones that you put into solution, find that conjugate base and form our weak acid. So now it's essentially been neutralized. If we were to throw some hydroxide in, it would find the hydrogen part of our weak acid, and it would neutralize to water, leaving behind just the acetate ion, which is also very weak. And so instead of having strong acids in our solution, or strong bases in our solution, all we're left with is weak acids and weak bases, which don't change the pH a great deal, because we're not producing a whole bunch of protons, hydronium ions, or hydroxide ions. And so that's why it resists the change in pH so well, is that essentially you have these two puzzle pieces that allow connection with protons or connection with hydroxides and neutralization to happen instantaneously whenever you add either an acid or a base. Pictorially, here's another couple examples of the exact same reactions. This is kind of examples in your book that really go a little bit further and pictorially explain what's happening. So whenever you add that strong acid, so hydrochloric for instance, hydrochloric binds, chlorine binds with your sodium to produce your acetic acid, which is weak, so it's not a problem, and sodium chloride. Whenever your strong base is added, water is produced along with sodium acetate, which is a weak conjugate base. So then, why do you think most buffer solutions contain two dissolved components? Go ahead and write it down. Think about it here for a second. Alright, I hope you came up with something like this. The weak base component neutralizes any incoming acid, and the weak acid component neutralizes any incoming base. If you only have one of the two components, then it's not going to be able to neutralize the opposite acid or base. And if you have a strong acid or strong base that's making up your buffer, it's not going to work because the strong acid is just simply going to completely dissociate, and it's not really going to do its job at neutralizing the incoming base. And so you have to have both a weak base and the weak conjugate part of the so if you have a weak base, you have to couple that with a weak acid. Weak acid, you have to couple with a weak base. And so if you got the acid, you need its conjugate. If you get its base, you gotta have its conjugate. And so really you have to make sure you have those two components, or it's not gonna be able to do its job. And its purpose, its job, once again, is simply to resist change in pH. But what it's composed of is your weak acid, conjugate base, or vice versa. So here's an example of a good buffer solution. Your blood contains several buffer solutions, and the whole point of your blood acting as a buffer system is to maintain your pH between 7.35 and 7.45. Outside of this range, your proteins become denatured. What does that mean? Denatured is just a fancy word for meaning unraveling. And basically proteins, they exist and they're able to do their job well because of the fact that they have the shape and the form. It's like a car. If you denature a car, that means you take all of its pieces and you pull them all apart. How good does your car run if it's pulled into a bunch of different pieces? It doesn't. It just stays in the shop and collects dust. Your proteins are the same way. They have to do their job. If they can't do their job, you're not going to survive. And so, in order to maintain the proper structure and maintain its proper function, your blood pH has to exist between 7.35 and 7.45. And so, one of the systems in the blood that helps maintain this pH is the carbonic acid sodium bicarbonate system, which is very similar to our acetic acid solution, except for we're using a different weak acid and a different conjugate base, that of carbonic acid and sodium bicarbonate. And it works the exact same way as the acetic acid solution. If something in your body is trying to increase the pH, your blood's going to take care of it. Same thing if something in your blood's trying to decrease the pH. Either way, it's going to be taken care of. And so that's why I laugh a lot at some of these like natural waters that are like, oh, we're going to increase your or decrease your pH, blah, blah, blah. I'd be careful about those kind of claims, because your body is doing a beautiful job of maintaining the proper pH without all these crazy claims getting in the way. If you needed an external product in order to maintain your blood pH, we'd all be dead, because the second that you aren't eating or consuming whatever that item is, it would be the second you die. So basically, the blood is a beautiful example of something that already does a fabulous job of maintaining the pH in our body. Within our body, there's a whole bunch of different components, a whole bunch of different buffer systems, and it's just what's the range that we need. The carbonic acid sodium bicarbonate solution system works great in this range of 7.35 to 7.45, but different buffer solutions operate at different pHs, some high, some low, and so that's just kind of how buffer solutions work. So it's kind of a quick lesson, but I hope you kind of have learned from it, is that a buffer's whole job is to resist change in pH. Whenever an acid loses a proton, it produces a conjugate base, and the buffer is composed of a weak acid and its conjugate base. So you kind of have those two things working together in order to resist the change in pH. So strong acids and strong bases cannot be used as buffers, since they completely dissociate, and that would leave nothing in solution that can react with future additions of acids or bases. So a buffer has to be composed with the weaker forms of acids and bases in order to do its job, which is to resist changes in pH.